Hello, if you're watching this video, this is preparing you for the final exam. You must have made the decision now to take the Chem 110 final exam. So we're going to review the entire semester of chemistry, and I would suggest that you have paper, pencil, calculator ready. Be prepared to pause the video so that way you can work some of the problems here. Now remember that chemistry is the study of matter, anything that has mass and takes up space, and energy. And so the first thing you need to be able to do is recognize when matter is undergoing a physical change or undergoing a chemical change. See if you can identify these right here. All right, so how'd you do? Did you say that crushing was physical, that burning was chemical, that tearing is physical, rusting is chemical, baking is chemical, baking or frying, and then of course chemical reactions show those chemical changes, and we've studied a lot about chemical reactions. How are you on these states of matter? Take a moment and jot down what characteristics each state has. All right, so hopefully you thought of solids with a definite shape and volume, liquids with a definite volume but taking the shape of their container, gases with no definite shape or volume, and then plasma like a gas, only charged particles. We then went on to study most matter, how it exists in nature, and that is as a mixture. Either homogeneous or heterogeneous, like even the air that we're breathing right now is a homogeneous mixture. And what does all of these changes, either physical or chemical, or even nuclear, need to follow this law of conservation of matter? And what does that law tell us? Hopefully you were thinking that that law tells us that matter cannot be created or destroyed, only change from one form to another. So if we have solid ice, water, in other words, and it melts, we still are going to have that same amount of water, that same number of water molecules, but in a different form. All right, how are you on measuring? Words like accuracy and precision, knowing the SI units. Well, accuracy and precision, you will need to know. Remember, accuracy is how close to the actual value, and that's how I remember that, accuracy and actual value. And precision is how consistent your measurements are. Can you look at those numbers there and identify the correct number of significant figures? Hopefully you said 5 for the first one, and for the second one, 2. Then 8, then 3. Remember, zeros are what you'll need to be cautious with when working with significant figures. In that first example with 5 significant figures, the decimal point there makes all of those zeros significant. And so does 3.00000010 with 8 significant figures. Leading zeros, as in 0.0089, are not significant even with a decimal point. And then as you're doing calculations, you need to always round to that correct number of significant figures. So as you know, water has a density of 1.0. If an object floats in water, what would its density be? Hopefully you were thinking that it has to be less than 1. Less than the density of water. All right, let's practice some of these vocabulary words. What would you say? Hopefully you said accurate. Hopefully you said precise. All right, what is density then? Well, density is the ratio of mass to volume. We've used it several times this semester. It has units of either grams per milliliter or grams per centimeter cubed. Many items are compared to the density of water, since the density of water is 1. The whole SI system was, of course, designed with water in mind. All right, so what about this one? Can you do this calculation? Another great time to pause the video. All right, how did you do? Hopefully you started with the density formula, and then you simply substituted in the information given. then did the math. I came up with 10.77 grams per milliliter per milliliter. And one of the things that I've noticed as I've been reviewing your work this semester is if these were your 4 choices, which one do you pick? And so I'm thinking that as you're looking at choices like this, some of you are thinking, oh, there must be a typo here. No, there's no typo. The correct answer here is actually going to be 11. And so that's what you would need to pick. All of these others are correct, but they're not rounded to the correct number of significant figures. Keep in mind that in your problem, the least number of significant figures was 3. Since you're dividing here, you're going to need, or 2, excuse me, not 3, 2 significant figures. You're going to need to round your final answer to 2 significant figures. And of course, this object will sink since it is much greater than the density of water. Now, of course, if you calculated this density, and here's another one for you. And of course, this one is also going to sink. Okay, so you will need to know different types of materials and how they exist. This is a flow chart that I have mentioned to you a couple times during the semester, so you need to know where pure substances are, that pure substances are simply elements and compounds, and that most matters existing as mixtures, either homo or heterogeneous mixtures. So let's see if you can identify these various types of materials. I believe there are 6 questions here. So we're just going to go through them, and then you're going to jot down what they are. What would you say this is? How about number 2? Number 3? Number 4? Number 5? Number 6? Could you give an example of number 6? All right, so what'd you say for number 1? Hopefully you were thinking elements made up of atoms, which cannot be made any more simple. These are the smallest particles of matter we can have that still retain the properties of that material. For example, oxygen make up oxygen. And so you can look now at an oxygen atom and know what that is. Don't forget Avogadro's number, that if you have a mole of oxygen atoms, we know how many atoms, 6.02 times 10 to the 23rd atoms. All right, what about this one? Hopefully you said heterogeneous mixture because it has different layers. How about this one, number 3? Hopefully you said homogeneous mixture, like a solution. Solutions were one of the homogeneous mixtures we spent some time studying this semester. How about number 4? Hopefully you were thinking of a compound, specifically an ionic compound. So you're going to need to know about those ionic compounds, how they're made, how to write their formulas, how to name them, and their properties. Hopefully for number 5, you said covalent compound. Sharing is caring. How about number 6? Hopefully you said polyatomic ion. Keep in mind with this is multiple atoms bonded together in a covalent bond. And this is a little different than a monoatomic, like if you had a single ion, like Na+. And for your example, did you come up with something like sulfate or phosphate that we've studied this semester? All right, make sure you know all the parts of the atom. The various scientists who did discoveries, especially Rutherford and Thomson. Be sure you know the periodic trends, that you can look at a periodic table and tell those, and that you can comfortably do electron configuration. Use that electron configuration to figure out the total number of electrons and the valence electrons. So for this one, our highest energy level here is going to be S. So this one's going to have 2 valence electrons. its total electrons, if I just take each of these superscripts and add those up, I've got 10, 24. So with 24 electrons, as long as you can then figure out what atom it is. We don't usually use electrons to do that because atoms can, of course, gain and lose electrons, as you know. All right, so what element is this one? Hopefully you're thinking 11 electrons. That must be a sodium atom if it with all of its electrons and each electron in the ground state. You'll need to know a lot of vocabulary words like this one. Hopefully you're thinking a Lewis dot diagram. You're exactly right. An example would be sulfur. So how do you draw a Lewis dot diagram for sulfur? Hopefully you're thinking, okay, well, 6 valence electrons. I'll take the symbol S for sulfur and surround it with 6 valence electrons. And you're exactly right. What number represents 1 mole? Hopefully you were thinking of Avogadro's number, 6.02 times 10 to the 23rd particles. Or if I have 1 mole of a gas at standard temperature and pressure, it's going to take up a volume of 22.4 liters. What subatomic particle has which ones have an electrical charge? Hopefully you're thinking our positive protons and negative electrons, and our neutrons have no electrical charge. How about this vocabulary word? Yes, hopefully you said isotopes. For example, some carbon atoms could have a mass of 14 while others have a mass of 12. And that's because the carbon atoms with a mass of 14 have 8 neutrons, where the carbon 12 atoms each only have 6 neutrons. All right. Which scientist was this? Hopefully you were thinking Rutherford with his gold foil experiment. What type of ions do metals form? Hopefully you're thinking positive ions. Metals only want to give away electrons to form those positive ions. Like calcium would want to give away 2 valence electrons because that's what it has. It's an alkaline earth metal in group 2. And so it would try to give those 2 valence electrons away. What do we call those large numbers? Hopefully you're thinking the coefficients. For example, if we were making water from hydrogen and oxygen gases, we would need to balance that equation with some coefficients of 2. What are the periodic trends? These were all ones that we looked at: atomic radius, electron affinity, ionization energy, and electronegativity. Be sure you review how those change. The biggest mistake I see people making is with atomic radius, because it's counterintuitive that as you go across a period on the periodic table, that your atomic radius decreases. All right. Which element has 20 protons? Hopefully you're thinking calcium. Make sure you know about ionic compounds, covalent compounds. Make sure you can figure out the charges of ions, and that you review writing the formulas of the compounds. If there's a monoatomic ion, it's very simple. Polyatomic ions will be given to you, so that makes them simple as well. And be sure you recall that crisscross method that we use when writing ionic compound formulas. All right. Take a moment and see if you can figure out the charges of those various elements there. What charge would they tend to make based on their position on the periodic table and their number of valence electrons? All right, how'd you do? Did you get them all? Now, of course, iron being a transition metal filling its d orbital, I would have to tell you whether it was iron 2 or iron 3. All right, what about if we had an ionic compound with lithium and oxygen? What's the name and the formula? Hopefully you were thinking that lithium and oxygen would make these ions +1 and -2. Use your crisscross method and take those charges and just crisscross that. So next to oxygen, there's like an imaginary 1. Next to lithium, there's a 2. So you do need to have those subscripts there. And that our name here would be lithium oxide. How about SiNO? This one is covalent. 2 nonmetals. Hopefully you were thinking what these look like with their Lewis dot structures, and that you would need 2 oxygens for 1 silicon. So they could have each have their octet. And our name, of course, silicon dioxide. Need those prefixes with those covalent compounds. What type of compound would have a high melting point? Hopefully you're thinking ionic compounds have that high melting point, whereas covalent compounds have that low melting point. This rule right here. Hopefully you were thinking the octet rule. All right, then we've talked a lot about chemical reactions. So you're going to need to know what chemical reactions are, what all of those symbols represent, how to balance them, and you will need to know the various reaction types. So if you want to take a moment, pause the video and review that, that is a great suggestion, because then we'll have some practice with those things. All right, so what do the symbols mean? Hopefully you're thinking, well, that means aqueous, it's dissolved in water. Solid, gas, yep, and liquid. All right, so what type of reaction? Hopefully you're thinking combination or synthesis. There's one product. How would you balance this reaction? Hopefully you're thinking, just like we had seen previously, that you're going to need a 2 here, add that coefficient of a 2, and that 2 there. So that way you have 4 hydrogens on each side and 2 oxygens on each side. What type of reaction here? Hopefully you're thinking a decomposition, since there's one reactant and multiple products. How would you balance this reaction? So once again, you'd have to add some of those coefficients. So let's see, I know I'm going to need 2 here. And if I put a 2 here, I think then I've got 2 C's, 4 O's, 4 O's, 2 AG's, 2 AG's. And that balances that reaction. Hopefully you're thinking, oh, that's got to be a double replacement reaction even before you see the products. You should be able to predict the products of reactions. And how would you balance this reaction? Hopefully you're thinking, well, we're going to need a 2 here, since our carbonate polyatomic ion stays together, we can balance it together, CO3, and then that looks pretty balanced. Again, what do we call those large numbers? Of course, those are our coefficients. Be sure you review the molar quantities when we go into finding the quantities of chemicals used in reactions. Can you find the molar mass of Ca3PO4? And can you do stoichiometric calculations? You're going to need to be able to do all of those. Did you get 310 for the molar mass of calcium phosphate? All right, how many moles? Great time to pause the video. Hopefully you were thinking, okay, to go from grams to moles, I have to divide by my molar mass. Calculate the molar mass of AgCl at 143. Notice that your grams are going to cancel out here. and you're going to be left with moles. That's important to use those units as a guide. And then simply do the math. So 2.001 moles of AgCl, and I can leave it right there at 4 significant figures. All right, what if you have 35.4 grams of copper? How many copper atoms, and those are going to be atoms there since copper is just an element, a pure element, are you going to have? Great time to pause the video. All right, how'd you do? And then after you've canceled out all of your units, always a good idea, you're left with particles. Do the math, 35.4 times 6.02 times 10 to the 23rd divided by 63.5. Hopefully you got something like this. Again, with these numbers in scientific notation, always be careful typing those into your calculator. Don't type times 10 to the anything, type second function EE. Some more vocabulary. What do we call this number? Hopefully you're thinking Avogadro's number. You're exactly right. Can you figure out the charges? What's the charge of Na, H, C, and O in this compound? How about this one? Let's be iron 3 oxide, potassium chromate, zinc, aluminum chloride. Pause the video and figure out the charges of each. All right, how'd you do? The first one's a little tricky. The second one, all you've got to really do is uncross it. So that 2 was there, that 3 was there. For this first one, those are tricky for me. So I'm thinking, okay, so that's got to be a -6. Because oxygen's always -2. I know that sodium is always +1. So that means that, and hydrogen's either +1 or -1. So in this case, my hydrogen's going to be +1. So to equal 0, because compounds, just like atoms, have to have a 0 charge, they're neutral, that this has to be +4. So hopefully that helps you. How'd you do on this next one with a polyatomic ion? Of course, the plain elemental zinc would have a charge of 0. And then aluminum chloride. Should have been an easy one. And we're going to look at those charges to be able to figure out oxidation reduction reactions. The acronym I like to use is OIL-RIG. Oxidation is loss. Reduction is gain. When something loses electrons, it's oxidized. If it gains electrons, it's reduced. And so in something like this, you can figure out the charges of each species and then figure out what's oxidized, what's reduced. So take a moment, pause the video, and do just that. All right, how'd you do? Hopefully you figured that copper starts as 2+, goes to 0. So obviously its charge is being reduced. Our oxygen is staying the same, so it's a spectator. Our hydrogen went from 0 to 1+. So it is oxidized, whereas our copper is reduced. So a couple things you need to remember when working with oxidation reduction reactions. If you have a plain element, its charge or oxidation number is 0. But like, what would be the charge of this hydrogen in HNO3? Well, I'm going to figure it out the same way I did before. So I'm going to say, okay, so my oxygen is -6. My hydrogen has to be +1 or -1. So that means it's going to have to be +1. And this nitrogen is going to have to be +5. So that hydrogen nitrate, nitric acid, in other words, is going to have a charge of 0. Taking a look below, what's oxidized, what's reduced? Hopefully you figured out that the zinc was oxidized, the hydrogen was reduced, and there was no change in the chlorine. Remember about gases, we spent a long time studying gases during the semester. Remember, they have no definite shape or volume. Their particles are very tiny with large spaces between them. You always have to convert your temperatures to kelvins. 1 mole of a gas at standard temperature and pressure is 22.4 liters. All right, let's do a quick gas law review. You'd want to number that paper from 1 to 7. I have quick 7 questions for you. I'll show you the questions, and you should pause the video, work each one, and then at the end we'll check your answers. So for gases, you're going to need to know all the different relationships between pressure, temperature, and volume. You're going to need to know all the various gas laws. All right, here we go. Great time to pause the video. Here's number 2. Number 3. Number 4. Number 5. Number 6. Number 7. All right, how'd you do with number 1? Right. Hopefully you were thinking pressure increases, then that's Gay-Lussac's law. I like to remember that with toilet paper. Gay-Lussac uses toilet paper on his maypole, T and P, and that's an inverse relationship. Or I'm sorry, a direct relationship. Boyle's law is our inverse relationship. How about this one? How'd you do? Hopefully you were thinking that pressure decreases. There's our Boyle's law with our inverse relationship. Hopefully you were thinking Dalton's law of partial pressure. Hopefully you use that 22.4 liters to figure this one out. How'd you do on number 5? One of the things I sometimes do is look at the information that I'm given from a problem so that way I can organize it. A big mistake I sometimes see people doing is they might match this pressure with the second volume, for example. Because we're given no information about temperature for this 5th problem, we can actually drop it from our equation. There we go. Temperature is eliminated. You know this is Boyle's law, of course, PV. Boys play video games. And simply substituting everything in. Solving for P2 by dividing by 5, each side by 5. We get 1.28 atmospheres, and then round to 2 significant figures. All right, how'd you do with number 6? I'm just going through all my calculations here to get volume 2 by itself, and I come up with 1.2. I hope you got that as well. So how'd you do with number 7? For number 7, of course, you need to use the combined gas law because you have information on pressure, volume, and temperature. So hopefully you were already thinking that. And then simply substituting those numbers in, temperatures converted to kelvins, and figure out what your volume 2 is. I usually try to work out all that math and then divide both sides by what V2 is multiplied by. And so I got 2.3 for my new volume. All right, we also studied solutions. Make sure you're familiar with the solution terms. A lot of vocabulary in our solutions unit. Make sure that you know about dilutions and you can use the dilution formula. Also, be sure that you can calculate molarity. Molarity, remember, is the number of moles per liter of solution. All right, so take a moment, see if you can solve these two problems presented here. Great time to pause the video. All right, so how did you do on that one? Again, this first one, the dilution formula, is one where you've got to kind of look here and go like, okay, so I'm going to call this molarity 1, and I'm going to call this volume 2. I'm going to try to figure out my volume 1. I don't know what it is. And I'm going to call this one molarity 2. And so that's super important that you can kind of match those up. If you match up those quantities incorrectly, you will get a wrong calculation or a wrong answer. So from that 350 milliliters of 0.5 molar solution, I'm going to be able to make 0.5 liters, half a liter of 0.35 NaOH. So in other words, I'm going to pour 350 milliliters of that solution into a flask and dilute it down to half a liter. All right, how about this molarity? Now, of course, you're giving grams here, so the first thing you have to do is to convert to moles by dividing by your molar mass. Once you have moles, simply divide by the liters of solution. So you have to convert those milliliters to liters. And you come up with a 1.7 molar solution. And that's rounded to two significant figures because of the two significant figures presented in the volume there. All right. Here's another good solutions practice. Great time to pause the video. All right, how'd you do? Oh, sorry. All right, how'd you do? Oh dear, it erased my drawing. Hopefully you got 6 molar, 6.0 molar for the concentration of this solution. Then we studied energy and equilibrium. Make sure you know the types of energy, all the factors that affect the rate of a reaction. Be sure you can do calorie calculations. You will not need to memorize the grams of carbs and protein and fat. Also, make sure that you know about equilibrium, Le Chatelier's principle, things that cause shifts to equilibrium, and things that don't cause shifts in equilibrium. All right, so what type of energy here? Well, assuming that the blades of the windmill are moving, that would be kinetic energy, of course. What type of energy would our ball have here? Hopefully potential energy, you're thinking. The ball's been pushed up the hill, just like we sometimes do with chemicals, but it's sitting still. It's ready to move and do work. All right, then be sure you know about acids and bases, all the different pHs. Be sure you know about neutralization reactions. When an acid and a base react to produce salt and water. Make sure you know about buffers. There are chemicals that resist changing pH. Be sure that you can find pH, the hydrogen ion concentration or the hydroxide ion concentration. Make sure you know these formulas and quantities. Be familiar with titration reactions, which you should be, from lab number 10 in your lab report. Make sure that you know how to titrate something to do the calculation. So great time to pause the video and see if you can figure out the concentration of that nitric acid. All right, so how did you do? Did you use M1V1 equals M2V2, where 1 could be your acid and 2 could be your base? Or vice versa? And then solving for the concentration of the acid. Hopefully you figured out that it was 2.9 molar nitric acid. Then you could use that, of course, to figure out the pH. If you simply take the negative log of that, you're going to get 0.46. So very, very acidic, strong acid. Hopefully you're good on nuclear chemistry. Hopefully you know about alpha and beta decay. Alpha, of course, is that alpha particle that Rutherford experimented with in his gold foil experiment. And beta is just a fast-moving electron. Be sure you review the strength and shielding. Alpha particles, of course, you don't need much protection against them. Beta, I believe you need about 1 meter of water if you were underwater to protect you from beta. Gamma, you need quite a few feet of lead or concrete. Make sure you know the difference between fission and fusion. And can you figure out half-life? Take a moment, pause the video, and see what you can do right here. All right. So often when I'm doing a problem like this one right here, I simply like to do it the old-fashioned way. Instead of using an equation, I look, okay, so if I have a 10-gram sample, in one half-life, half of it is going to remain. So that would be a 5-gram sample. And of course, that's going to be 15 hours because that's what our half-life is. So that's going to happen in 15 hours. If another 15 hours goes by, so now in other words, 30 hours, I'm going to have 2.5 grams remaining. That's half of my 5 grams. Then if another 15 hours goes by, so that's going to be 45 hours, I'm going to have half of 2.5, so that's going to be 1.25 grams remaining after those 45 hours. Of course, you can do that with the equations as well, but to me, that's just a really simple, easy way to do that kind of problem. How are you on organic chemistry? You will need to know the functional groups. So as I'm taking a look at this, a functional group that's jumping out at me here is this OH. That's the first one that's jumping out at me. That is an alcohol. Of course, here's a COOH, a carboxylic acid. We've got some amines in there. So you'll need to know about the functional groups. You'll need to remember that alkanes have only single bonds. Alkenes have at least one double bond, and alkynes have triple bonds. You'll need to remember that cycloalkanes are when instead of making a chain, the carbons make a circle. You'll need to be familiar with naming those chemicals, those compounds. All right, there we go. The whole semester in one slideshow. I hope this helps you as you're studying and reviewing for your final exam.